Today on the bench I have my old friend, the Harman Kardon 730. This is a, let me see here. This is one of my favorite listening receivers that I use. I use this on my desk all the time. And when I'm not testing or test driving somebody else's receiver or another repair I've done, I revert back to this one. This one always puts a smile on my face because it sounds so good. And I was wondering, why does it sound good? And I was looking at the schematic. Well, it's very simple, very basic, and it's perfect to design, I think. Anyways, the problem this thing has is developed transistoritis. Now, on the right channel, it started doing the pop, fizzle, scratch, pop, fizzle, scratch, and it was coming out the right channel. So what I did is I stopped using it immediately, because if you continue using it when it's doing that, you could end up grenading one of the amplifiers. Now I don't know if it's happening in the preamp or the power amp, but it's definitely sounds like a transistor, and let's demonstrate it for you here. I got it hooked up to a pair of speakers, plugged into line cord, and I have the scope up, but let me just give me a second here, I'll get things set up. Okay, you should be able to see the scope up on the screen. Let's turn it on. I have hooked up the speakers. Okay. And there it is, coming out the right channel. Click the microphone to the speaker and you can hear it a lot better. You can see it's starting to really start to go to town when it warms up a little bit. It looks like it wants to go negative, which tells me that it's probably a power supply or power amplifier problem. You hear it, it's really going to town now. Funny enough, it still plays music fine through that channel. It sounds great, but it's got this awful hiss, snap, crackle, pop, fizzle. So, how do we determine where this is coming from? It's a very basic circuit, the power amplifier and the preamplifier. There's not much going on here. So let's break the connection between the preamp and the power amp, and we'll see if this goes away. If it does, we know where to start looking. I'm going to pull out the bridge connectors. Okay, here goes the right channel. That's left. Why is that left? Okay, so the connection between the two amplifiers is broken, and we still have our problem. So it's definitely in the power amplifier section. So let's go after that next. Shutting it off. Alright, here's a look at the power amplifier for the right channel. It's pretty basic, like I said. It's pretty minimal design. We have our input, differential pair or long tail pair, whatever you want to call them, and then it goes into a voltage amplification section, bias spreader, and then we have our drivers and final outputs. So where is this happening? We don't know yet, but we're going to figure it out. It could be anywhere. I don't think it's the power output devices. I'm pretty sure we're safe with those. Could be a driver. I noticed that when it's wigging out, the signal's trying to go negative. So maybe this transistor's failing, Q413, or it could be something in the bias spreading circuit, or it could be something in the input circuit, the long tail pair. So let's go through and probe all these points, see if we can determine where this noise or this fault is coming from. And just for the record, these two transistors at the front end here are not 2SD 415s. They are actually 2SC 1400s, and those are known bad transistors. They're on my naughty list. So they're probably my first suspects, is one of these two transistors. Maybe it's this input transistor or the feedback. I don't know, but we're going to figure it out here shortly. So let's see if we can diagnose where this problem is coming from. Let's poke around with a scope. What I have my current arrangement is the top trace is my probe. You can see here I'm going to probe around with a yellow trace, and the bottom trace, the blue trace, is the speaker output. So you should be able to see what's going on there too. And what I've done is I printed up the schematic for myself and blow up the camera here. And actually, you know what? I made a mistake earlier in the video. I said it was the right channel, but it's actually the left channel. I just had my speakers wired in reverse when I was listening to it, and came out the right channel, right side. The left channel was making the noise. So left channel, all the even numbers in the schematic, C40, 410, 404, 402, all the even numbers are your left channel. Okay, so let's start probing around here, these two transistors, your long tail pair, and see what we can see here. If we find nothing, we're going to start working our way through the circuit until we find where the noise is coming from. So let's turn on the receiver. And here comes our noise. So first transistor is Q402. Let's look at the base. Right up top here. It's going to be hard with a camera in my face. So let's try this one. And that's silent. Let's look at the emitter of Q402, if I can find it here. The board is marked, but it's not marked well. Let's see here. The emitter should be the collector 406. Let's look at the collector 406. That would be our can't get in there. Oh, now it stopped. That's not what I wanted to hear. I want to hear it keep going. Now I'm dead in the water because I don't have my noise. Will it come back? Was it something I touched? Something's solid. Base of 406. Let me just let this idle for a bit and see if the noise comes back. Can't really troubleshoot without the noise there, so this might be tricky. Stand by. Okay, this is embarrassing because I had full plans to make a video on how to troubleshoot this kind of failure or this kind of defect in your stereo amplifier, and as soon as I threaten to look at it with a probe, it starts behaving. So how do you deal with something like this? How do you deal with a fault like this that is not going to reveal itself? Well, you really can't. You can make assumptions, and you can go on those assumptions, and you can do your best. You can swap parts out, and then test drive it, and the fault comes back. Then you know you missed it, and you have to take another shot, right? But in this case, I am going to replace these two transistors, the long tail pair. They are 2SC 1400s, and they are on my naughty list for this kind of failure, for shot noise and what do they call it? Shot noise, leakage. Yes, let's replace these two transistors, and I'll replace the two in the other channel as well, because I want this amplifier to continue to sound balanced and clean with its output. So let's pull the amplifier out. Let's select a couple of transistors to use as replacements, and I have a good idea already that I'm going to use 2SC 1845s. I have plenty of them here on stock, and let's select a few of those transistors to put in. Alright, now that I got the power amplifier out of the receiver, we can give it a good look. Remove the heatsink, remove the transistors. Now, give all of these solder joints high scrutiny, because any one of these joints that are cracked can mimic the same symptoms as a bad transistor. If you have popping and scratching in one channel, it could be an intermittent connection, and it could be that's what your problem is. So go over this with go over every joint with a magnifying glass and have a good look. If you see anything that's got a crack or it doesn't look right, just reflow it. It wouldn't be a bad idea just to reflow it anyway, but that's where you would start. Let's say, for example, you pull this out, everything looks perfect, and you're sure it's a transistor, but you don't know which one. Well, if you can get the board to act up while it's under power, then you can test it. But if you don't, you have really no option other than to just start shotgunning parts that you might suspect, right? So here we have these 2SC 1400s. I got 1, 2, 3 here, and I got 1, 2, 3 here. And these are on my list of naughty list, and they are listed as, let's see here, they don't have anything beside it on my list. But what I'm going to do today is I'm going to replace them with 2SC 1845s, and I have all kinds of new ones here. And what we're going to need to do is we're going to need to find a matched pair for here and a matched pair for here. This one here on its own, Q405, 406. Where's my schematic? Q405, 406, this one down here. This one's not critical, but we're going to replace it anyway. This might be a problem too. So we're going to replace these three transistors and go from there. 410 is 2SC 85. This thing doesn't have that many transistors. I don't know where they're getting them from. Oh, there they are. Okay, these ones. You know, it very might well be that these are fine, and it might be something else, like this bias spreader transistor, or it might be one of these diodes. The bistors, I think they call them, the double diode. There's one here and one here. These are kind of temperature sensing. So let's go through this, and let's start with the left channel. Let's remove one of these transistors here and see what we can get. All right. Okay, let's test this in my transistor tester. Now, if you have one of these little testers, these Chinese testers, all the better, but if you don't, it's not a big deal. I'm just putting it in here to test it to see what gain it reads. Let's see what we got for gain on these transistors. And let's fire this thing up. You can't see that, can you? So I got a gain of 438. All right. Now, I was looking at these replacements. They have a gain around 370, slightly lower, but it should still do the trick. Let's try one of these. Let's close this up, try it. Yeah, 388, and I said 370. So not too far off, but we will want to get a matched pair. So let's concentrate on getting a matched set of these transistors. And how do we match them? Well, we can go through and measure, just put them in a circuit and measure their characteristics, and then from there we can match them that way. We don't have any fancy test equipment. It's just a simple circuit we can build with 4 resistors and the device under test and a power supply. So let's go through and do that. All right, so let's draw our circuit. We've got our device under test. And all right, so what we want to do is we want to set up a circuit that puts this under a real life condition and creates turns the transistor on and shows up how much gain it has. So what we can do is we can put a resistor here and a resistor here. Okay, this one can be 10K, this one could be 1K, and this is 1/10. And we'll take our measurements from here to here. I have a voltmeter, okay, and this will be our power supply, plus, minus. And let's bias this transistor. So let's get a resistor here and a resistor here. All right, so since we have this resistor 10 times larger than this resistor, let's make this the same. We could do this with, let's try 33K. And then we can do this with 330K. Okay. And that should put our device under test, and it should actually put a load on this. If power supply, we could use anything that's going to turn a transistor on, anything larger than maybe 3 volts to, what are these 1845s rated? I don't know. They're like 60 volts or something. I'm not sure. Don't quote me on that. But we want to put it under real life conditions. So let's go a little higher. We don't want too much current through here. We have to be aware that if we put too much current through the device, we'll blow it up. And that is a function of voltage with this resistance here. If you turn the transistor fully on, you're going to have 11K of load, so that's going to limit the current. But let's, for simple sake, let's say 12 volts here. Let's just put 12 volts, and we'll go with that. And then we'll put our device under test, and then we'll measure our voltage. What we do is we test this transistor, record its voltage, take it out, put another one in, record its voltage, and we'll see how they compare. All right, so I built a little circuit here just as it's drawn, and I got my meter connected to the collector pin. It's emitter, collector, base, and I'm using these first 3 holes here on this 0 insertion force socket, and that allows me to put the transistor in, close it down, and take my measurement. Now, the thing about this is these transistors are temperature sensitive, so you can't handle them with your fingers, because as soon as you pick one up with your finger and thumb, they're going to get heated up by your body and they change characteristics. So I'm going to use tweezers to hold these. Let's turn on our voltmeter. Hope you can see that. And let's connect our power. I got our negative. I got 12 volts on the power supply. We should be able to read 12 volts when I connect this. Here it is. Okay. So let's take our first one, get it in the right way. I'll just drop it in here and close it. And you can see this one is 708. Now watch what happens if I touch this with my fingers. See how it drifts? Okay, let's try another one. Don't come up. Turn this one on. And this one's 7.716. That's dropping. 14. Let's go 14. 13, 12. The transistor heating up on its own. Seems to be drifting. Let's take it out. Next one. Oh, this is... I'm going to calculate the current through this because it seems like it's drifting as soon as I put it in. Maybe the transistor's heating up from the current going through it. This one's a 7 point... I'm going to say that's a 1.4 as well. Let's take this one out and put this one with this one. I think these ones are fairly closely matched. These two here. And this one's still out on its own. Let's try this one. That's another 1.4. So we got 3 of those. All we need is 2 matched pairs, which is 4 transistors. That's a 33, that's way out. Let's put that aside. $708, so 7. 7708, 06. Another one. $711, 14, 15, 16. See how it's changing? That's a 17. Okay, that one's out. Try not to handle these with my hands. That's okay. Ooh, that one's really far out. Okay, that's a no-go. But we have 3 here that are very close. Let's see if we can find a 4th one. 42, nope. 706. $43, nope. $12, $11, $10, $9, it's dropping. Let's see if we can find another pair. That's what I'm looking for. Nope. Might have to get some more out here. $14, $13. This one matches another one really closely. This one here, I think. But it drops like a rock. So it should only be 1.1 milliamps. There shouldn't be enough current there to do any self-heating on that transistor. Let's try this one again. I think these two are a matched pair. Yes. So we have our matched pairs. We have these two here. This one's out. This one's out. And let's try and find a matched pair here out of these three. These three are very close. $16. Okay. $16. Okay. Let's try the last one. $16. So any one of these will work. All right, so there's our two matched pairs for left and right channel. Let's put these in. All right, let's remove our old transistors. Make way for the new ones. I really wish that this would have cooperated. I could have made a video of how to pinpoint which transistor it actually is instead of just making guesses. But can't always have what we want, right? Got those three out. Let's remove these three. I'm replacing the ones in the right channel just because I want the pairs of transistors to be matched. I don't know if that's going to be important with sound quality. I think it will, but we're going to find out here. Remove all three of these, all six of these transistors. Okay, pull the last one. Just want to see how these boards are marked. Okay, so they are marked emitter, collector, base. So the same pinout. Okay, good enough. Let's get some flux on here. Clean this mess up. One way to check if your holes are open, just hold it up to the light, and if you see light through all your holes, you're good. Last one. Okay. Now I got these two I set aside. These are not matched pair. They are just regular 1845s. I'm going to put them in the position of Q405, 406. Emitter, collector, base. Just going to put these in, and I'm replacing those dodgy C1400s. Let's do this first. Okay. All right, those two are in. Okay, so I'll go grab a pair. Put these aside so they wouldn't get mixed up. Let's put these two in. Emitter, collector, base. Those are right. Double and triple check your pinouts. I think we're good. All right. Let's grab the other pair. You're probably wondering, why didn't you do this when you did the restoration on the receiver in the first place? Well, I didn't see a need to, because they were working great. The receiver sounded great. It had a fantastic, clean sound that was hard to beat. And I really enjoyed how it sounded, so I just left it alone. And I don't think every time we should be changing parts just because they're suspect, or they might fail. But in this case, we did have a failure. Now we're going to put this all back together, and our listening test is going to tell us if we are successful or not. So let me clean this board up, put it back together on the heatsink, and then we'll reassemble. All right, got this all back together. I got the board cleaned, torqued down these screws, torqued them all to the same relative value. Don't go crazy on them. I'm using sill pads on this one. Now, always check for shorts between your devices and your heatsink. Because if you don't, you plug it in, it'll grenade. Okay, so let's... Okay, nothing. We're all good. All right, it's ready to go back in. Looking good. That's what I love about this HK is it's so easy to service. You just pull the module out and put it on the bench, and it's easy to work on. All right, modules in, plugged in, time to power up. I'm going to test for DC offset on the outputs. And good place to check for outputs is right here on these two speakers circuit breakers. So I'm going to do one channel first. Got my voltmeter hooked up, let's turn it on. And it's going to settle. Settles at 25, 30 millivolts. Let's try the other channel. This one's at 18, 16, 17. I'm happy with that. So let's set up the bias. Let me check it first. Can't remember where to connect on these. Let me refresh my memory on where to connect my probes. I know it's across these two emitter resistors. So it would be collector to collector, wouldn't it? Yeah, let's try that. So let's go from collector to collector. Can you see this? You can now. 16 millivolts there. 33. Okay, we're going to set the bias up. I can't remember what the value is. Let me go look it up. All right, quick look in the service manual. It says 35 millivolts between collector to collector. And what do I have here again? I had 16. Yeah. So let's connect my probes. If I can do this with one hand without blowing up the machine. This is dangerous work. Okay. Come on, connect. Went the wrong way. It says plus or minus 5 millivolts. I'm going to set it to 33. Set this one as well. 34. Set it to 33. And we'll leave it at that. Power consumption, sitting at idles, 28 watts. Well, there you got it. It's back together. It's working, sounding good again. So I just want to do a few notes about this circuit that I just drew up out of the blue here. There's a lot more to it than this. If you want to do absolutely precision matching of transistors, there's a lot more to it. You have to check at different current levels and different voltages. This is just a basic static test. Now, this will work on any transistors. If you're doing PNP transistors, just reverse the voltage on your power supply. Okay, and this won't work for matching complementary pairs, because a complementary pair of a NP and PNP is well, they have different characteristics, and they won't match according to what this circuit's doing or trying to do. So they're only for matching similar transistors of a similar make. Enough about that. This is going on my listening desk now. I'm going to hear it for a while, see how it sounds. I think it's going to be all right. And if it starts acting up again, there's going to be a part 2. And hopefully it's not. That's the end of what we see here. So hopefully it's all good now. So take care. Hope to see you again in the next one. And thanks for watching.